Okay. All right, let's drag our way through this today. Oh, I'm not actually gonna drag. I'll try my best. I will leave every scrap of energy I have on the floor in here. So, we have a couple things to talk about today. The first is I want to talk about the polynomial section if we've got time, but I'd like to start by asking if anybody has any homework questions they'd like me to look at, because I think this homework assignment was quite a bit more difficult than some of the earlier ones. So,
use the forward direction on
3C number 6. Okay, hold on, let me pull it up. Prove that the dimension of the range of T is 1, if only if there exists a basis of V and a basis of W such with respect to their basis, all entries of the matrix of T equal 1. Okay, so prove that. This is 3D6. It says prove the dimension, prove dimensional, right?
Yes.
Prove that the dimension of T is equal to 1 if and only if there exists a basis of V and a basis of W. There exists a basis V, a basis W, so that the matrix of T is all ones.
Yes.
What's that? Oh yeah. Okay. So you want to start by assuming that the matrix, you want the backwards direction. So assume the matrix is all ones, show the dimension of the range is 1.
One of the forward direction.
The forward direction. Okay. So let's see, all ones. So that means you want okay, so let's see. So we're going to assume that the dimension of the range of T is equal to 1. And that means that it's a one-dimensional space, and so it has a basis consisting of one vector, right? So the range of T is the span of a single vector V. Not sorry, range W, right? W for W, and so the idea here is that every TV comes in. So the way that I would start thinking about it would be like, so let's actually start by thinking about how we could set up a basis here, right? So the naive way to do this would be to say, suppose that we pick anything we want for the basis of V, anything. We pick a basis of V.
For W or for
V, V1 through Vn. I'm just going to try to figure out how to start manipulating this map by writing down what it does. That's the idea I've got, right? I just want to try to figure out, understand what's happening by picking a basis for V. And then we're going to pick a basis for W that looks like, pick a basis for W that looks like W and then all the vectors that you get when you extend that to a basis for the whole space. I think it's a reasonable place to start, right? Yep.
So the W you wrote up
It's this
there,
W right here.
that is the basis for the range only.
This is the basis for the range only,
Then
right?
you
So
use the extension theorem.
yeah, let me use the extension theorem to get a basis for the rest of the space, right? So if you did this, what you end up with is it's kind of the right matrix, but not really, because you're going to get a row of ones and zeros everywhere else, right? Because with this setup, what you have right now is that, I mean, TV1 is going to be equal to, not going to be 1. It's in the span of this vector, right? TV1 must be in the span of W, which means it's equal to some constant times W. So like C1, W1. And so that means it must be 0 times all times W, and 0 times all the rest of these vectors. 0, W2, 0, W3, 0, Wm. And likewise, each basis vector here is going to end up with a different vector stuck to it. So this will also be in the span of W because the range is one dimensional, which means this is C2W plus 0, W2 out to 0, Wm. And that means in this, with these bases, the matrix of T is going to look like C1, 0, 0, 0 down here, C2, 0, 0 down here, C3, 0 down here, out to Cm all the way down here, right? Cn. So now, why am I starting out with like a wrong answer to the question? It's come to my attention from 2 or 3 people that like, as irritating as it is to have to write a matrix down, it's usually useful to do so when you're working on a problem with matrices. So you should try to write down the manipulation on the basis of the matrix itself, right? If you started with just randomly picking the first thing that came to mind, what would the matrix be? And this is what would happen, right? The fact that each one of these vectors is in the range, but those are spanned by one vector means they're all multiples of W, which means they must have zeros attached to the rest of the basis for W. Okay, so now the question is, how do you modify this? So I'd be curious, like, if anybody has a modification or what the answers were. I know that several people here have answered this question. Is anybody willing to offer their solution?
Oh, I said, okay, so I have the W1 in W such that W1 is equal to TB1 minus W2 and then minus all the way to W2.
Okay, so you have W1 is equal to TV1.
Okay, well, okay, so to start off, I have the V1 to Vm as a basis for V.
V1 to Vn is the basis for V, okay?
And then the dimension of the null space by the fundamental thing in linear maps is in V minus 1.
Okay. So yeah,
So
so the
then-
dimension of the null space of V is equal to MV, yep, minus 1. Sure. Wait, might we just write this as n minus 1? Yep.
And then that means that V2 to Vm are in null T.
So you're going to start with, okay, so this works. So what you're going to say is that like, you're going to find a basis for this space, which runs from V2 to Vn that are all in the null space of T. And then you're going to extend that with this V1 that's not in the null space. This is part of the direct sum thing, okay?
And
So
then
this vector is not in the null space and all of these are. That's what you're doing here.
I have
Yeah? I think that's what you're set up, what you're saying you're set up?
V2 to Vm.
Whatever, okay.
But
I'm gonna try to
Well, yeah.
translate this so I can be consistent with the way the
and
book is.
then, so T of V2 to Vm is equal to 0.
Yeah.
But T of V1 is not in the null, so it doesn't equal 0.
Yeah, T of V1 is in the range, or
So
T
it's in,
of V1 is not equal to 0. Yep.
so that means it's in.
So it's a non-zero element of the range.
Yeah.
Okay.
It's in, yeah. I put it in.
The TV1 is in the range of T and TV1 is not equal to 0. Okay.
And then I said, then we expand TV1 into TV1 W2 to Wn.
Okay, that's this. Okay.
And then let W1 in W be equal to TV1 minus W2 minus all the way to W.
Oh, that's cute. Okay. How are you going to get the next one?
The next one.
Well, you have a lot of vectors, right?
Well,
So,
like,
so what you're saying right now is that
like
you,
take,
so you have a basis that looks like TV1, W2 up to Wn.
and then let a W, like an element in W. Like, set that W, yeah.
Uh-huh.
Like, let W be in W,
Uh-huh.
and such that W is equal W1 minus W2 minus all the way to Wn.
Okay.
And then, I said, we want to show it's linearly independent because.
What's linearly independent?
That W1 to Wn is linearly independent.
Where's W1?
W will,
See, I think that the problem here is that if you're going to construct a basis, so this looks like it's along the right tracks, but if you're going to try to construct a basis for all of W, so that T of each of the V's ends up being one of each of the vectors, right? Then the problem is you've given me one vector W. You told me you've got this basis with TV1 in it. This is the same basis I constructed with a matrix. It's just a matrix of ones across the top and then 0, right? So if you're going to try to take, so do you have more than just the W idea here? Are there more vectors? Because this is a single vector. Certainly you can construct this.
well, yeah, like what I want to show, like, if you add, if I have W defined as 1 minus all of those.
Uh-huh.
then, like, I was thinking that W plus, like, not plus, but W with W2 to Wn, I said you want to show that, like, you want to show that there's a basis for W, like the space W.
Uh-huh.
And then,
But I guess I'm not really seeing how, if you have a list of M vectors right here that's a basis, and you've constructed a single vector, how are you going to get the rest of the basis? I don't see how you're going from this one vector to a reconfigured basis, like where you're going to tell me something like a new set of W's that are built out of the W2 to the Wn that are going to do this, right? Does that make sense?
yeah,
So you need to say more than, hold on, I'm trying to pull the book up so I can look at the question here. This was question, which one was it? 6 on 3C. Okay, so, okay, I'm gonna assert then that I think that the problem with that is that it's not that I don't think that you're going the right direction. I just don't quite see how you're gonna take this vector and turn it into a basis for all of W. Right? Because a single vector it can be part of a basis, but like what's that you say that you want, and for those of you that are doing this sort of approach to the problem, the idea is like this vector by itself. I mean, so you're saying any V, so here's what I would see, like if I was going to apply T to V and get something in W, sure, everything in W is going to be written in this form, right? Every output from T is going to look like this, right? The problem is that like, where all these are going to be 0, but in the matrix, that's going to give you a bunch of zeros if you do that. So unless you're careful about the way you sort of spread the TV1 out in the basis elements, you're not going to be able to get the ones that you need in the column. So my question is, how did you get the ones in the matrix? Because that's really the goal here, is to show that for that really what you're trying to show is that TV1 is equal to 1 W1 plus 1 W2 out to 1 WM. This line right here, if that was true for any V1 that you put in, that's what it would mean for the matrix to be a matrix of 1, right? So you need to construct a basis so that this statement is true. And yet that the vectors are linearly independent from each other. So then my question is, okay, so do you have another step to go after this? Is the question. All right, so what is the next step after this? So you got this W.
Then I said, like, then that means that TV1 is equal to W plus all of that. Like W plus, or I said after that, I said we want to show that W1 to Wn is linearly independent.
I don't see where W1 is.
W1 is for.
Yeah, no, but what in the thing that you built here is this W1? Is this W1? I'm not sure where W1 is.
Well, W1.
Because you tell me that you want to base this W1 through Wn, but I don't see what I'm supposed to do to, I don't see where you have to tell me. I mean, what is W1? I mean, I wrote it, but I would write a statement like this if I had defined. This is one of these things. You have to exhibit the exact method for giving me the W1, the W2, and so on that makes this happen, right? So you have to tell me, so like, where is the W1 in the picture? That you did?
Well, I think the W1 is
This is W1. Okay. So should we read, if you're gonna, are you gonna like generate a basis by doing this idea over and over again or adding things together? Well, I'm not trying to confuse anybody. No, I think the idea does work. I think the idea here is that once you have this thing stacked up, if this is the first thing that you want to start with, I think that the idea here is that you can generate a basis. I think you can, but the problem is when you're done with the basis, you actually need to show me like where the rest of the basis is. If this W1 is supposed to be in the front of the basis and all the W2s are the same, are you then going to construct? I mean, is this the basis? Is the basis for W equal to W1 as defined right here, and then the already existing W2, W3, and so on? Because you have to tell me the basis. I think this is what you're trying to do. I think you're trying to replace. You're trying to make a basis where it's okay to do this because these vectors will be linearly independent because these are all the null spaces. So you can stick W1 right here in place of TV1. I think that's what you're doing. Now, are you going to construct a basis for V?
Yeah.
Okay. So, all right, let's keep going. What's the basis for V? Anybody else is willing to, I'm not trying to dominate the conversation here. What's the basis for V? I have an idea.
Well, I have like I said, like V1 prime is equal to V1 and then so they is equal to 2 to M because then you can like argue thought that then if you apply T to both of them.
Okay, so what you want to do is this. You want to say in the first spot for V, keep V1. In the second spot, take V1 and add it to V2. In the third spot, take V1 and add it to V3, and so on out to V1 plus Vn. Why does that work now? Did you actually conclude? So now we're getting places. Now we got two bases, right? We got a basis for V and we have a basis for W, where this thing right here is defined to be this equation right here. Right? That's kind of where you're going with this. This is does anybody else have this idea, by the way? Look familiar at all? Okay, keep going. This is this is on the right track. I think this is going to work.
Then T of
What's T of V1?
I had
Expressed in terms of this basis.
W1 plus, well, T of V1 as W1 is defined up there as W1 plus W2 plus all the way up to W10.
This is something I said had to be true for the matrix to be true, right? The problem here is I want to know why it must be the case that if I take T V1, why is this true? Why is this 1 W1? Where does the 1 on the W2 come from? Why does that have a 1 in front of it? Because in your construction, I see what you're doing here. I mean, what you're doing is you're trying to force it to be the case that every basis vector has a V1 inside of it. Because if every basis vector has a V1 inside of it, that means this TV1 is going to fall out all over the place. Every expansion is going to have a V1 inside of it. This has a V1 inside, this has a V1 inside, this has a V1 inside, and so on. My question is, and all these are the null spaces, so they all get sent to 0, right? So then my question is, why does that mean? That tells me that at least one element of the V1 spits out a 1, but I have to expand TV1 in terms of this basis. And so again, my question is, why do these have to have 1s attached to them? Yep. So let's see. So TV1 is equal to, well, we know what TV1 is equal to. It's in terms of this basis, it's something like C1W1 plus C2W2 CNWN. That must be true, right? I mean, it's in the T of V1 is in W, and so it can be written out as an expansion in terms of W. The W1, the way you have it set up, is equal to this. So you could write this is equal to C1 times TV1 minus W2 minus W3 minus WM plus C2 W2 on the way out. So this is equal to C1 TV1. Okay, now right there, what does C1 have to be? 1, right? Because if TV1 is going to spit out a TV1, there better be a 1 stuck in front of it, right? And then let's look at the rest of it. What happens to the rest? Well, I've got a minus C1 W2 and a C2 W2, right? Plus minus C1 plus C2 W2 plus minus C1 plus C3 W3 out to minus C1 plus CM WM. But if C1 is 1, now this is where you get to, I mean, this argument is a little complicated, which is why we're spending time on it. Once you've sort of cooked up your trick basis by saying this is going to go right there, what do you know about what this particular linear combination? I mean, this is equal to TV1, right? So one way to make this true would be to put a 1 right here and a 0 in all the rest of these. Is there any other way to make it? Can I come up with any other linear combination of this vector and the W2 and the W3 of the WM that make this equal to TV1, other than saying this must be 1 and that must be 0 and that must be 0 and that must be 0? Is there any other linear combination of these guys that will equal this? Why not? There's a big fact here. Yep. It's a basis. Yeah. Expression in a basis is unique, right? There's exactly, as soon as you write down that C1, 1, and all the rest of them equal to 0, give you TV1 out. There's no other way to do it. This is a basis. Well, what does that mean about all the rest of the C's? C1 must have been 1, but that implies that C2 must have been 1, because if that's a 0, then minus C1 plus C2 is 0. And if C1 is 1, then C2 must also be 1. Which means that C3 must also be 1 because C1 is 1 and minus C1 plus C3 is 0. So C3 is 1 and all the way down the chain. And that implies all of the CIs are equal to 1, which means the matrix has a matrix of 1. Good job. And thanks for putting up with my grilling. Okay, so the idea here, so this, this is not an easy question, I don't think. There's a couple of different approaches to this, but the idea of like hooking up the trick basis and the reason why there's so much work on these matrix problems is that manipulating the matrices by manipulating the bases is one of the real key tools of working with this stuff. Okay, the insight, if you think like there's no way in hell I ever would have come up with this on my own, right? The idea of an argument like this is if you want to figure out like what the logical move for the discovery of the idea is. How can I build a map where the outputs involve TV1 everywhere? And this is what does that, right? The fact that we've got this TV1 involved in this step forces like everything to cascade down. Okay, so almost all of these matrix manipulation problems involve some kind of trick basis like this. Okay, yep. The W? This guy right here? Okay. So the idea is, say you just started naively and you didn't understand what was happening and you just said to yourself, okay, to me, this is an obvious idea. That idea seems obvious, right? Like, well, it's a one-dimensional space, take something that's not in the null space, feed it out to the range and build a basis like that, right? I mean, if the null space is n-1 dimensional, then the range must be one dimensional, which means the span of one vector. So find something that's not in the null space and throw it over there to be the basis for the range, right? So if you write this down, the problem is that you get that sort of row of ones problem that we had before, right? Everything is in the range that gets mapped to the range, that gets mapped one dimensionally. So it's either 0 or 1. The problem is, how do you get all of the rest of these ones? I want this to be true. I really want this line to be true. I need there to be ones in all these places. And I need that to be true for any v that I put in. So the idea of subtracting these away comes from the idea like, I know there has to be a C2W2. That has to be there. I mean, this is a vector in W. I have to expand the output of T in terms of the W basis. So if I need this to be here, and I need there to be a 1 here, I'm going to have to somehow get this vector involved in this vector. It has to appear twice in the equation for there to be a 1. Otherwise, there'll be a 0. Because those vectors like represent the part of the space that isn't hit by T. So the game is that, you know, if I want there to be ones, if I want this to be true, then it had better be the case that whatever this vector is involves W2 in some way. If you do that, then you're going to end up with a matrix that has ones across the top or constants across the top and 0 everywhere else. And the reason that you get all of the rest of the ones in here is you have. Here's the best approach to a problem like this. You're doing a question like this and you have no idea what to do. Okay. And I've pointed this out to a couple of people already. Do it in the 2 variable case. Just imagine that you have a map T. It goes from a 2D space to a 2D space. And let's suppose that the range of T, dimension of the range of T is 1. It's a lot easier in a lot of these problems to figure out what to do if you look at very small examples, right? If you look at this problem and you say, okay, well, naively, let's just pick a V1. Okay, the first thing you should say is, well, I know if I know the dimension of the range of T is 1, that means the dimension of the null space of T is also equal to 1. So I might as well use that fact somehow, right? If I'm given this information, typically I'm going to be using this theorem somewhere, right? So if the dimension of the null space of T is equal to 1, then that means V is equal to the span of, say, V1, V2, where V2 is in the null space of T. That's in the null space of T. I extend it to a basis for all of V by putting one extra vector in it. So what do I know here? I know that with this basis, T of V2 is equal to 0, and T of V1 is equal to, well, it's equal to TV1. It's not equal to 0, right? This isn't going to work because if the output is 0, then that means all the coefficients will be 0. I have a column of the matrix that has zeros in it, but this gives me a starting place. Now let's look at W. Well, W is equal to the span of W1, W2, where maybe W1 is equal to TV1. The range is one-dimensional. If TV1 is not in the null space, then it spits out into the range. And so this seems like a reasonable basis to start with. I mean, this is where your starting spot. I've got a basis for the output space where that's in the range. And I got a basis for the input space where this is in the null space. If you compute the matrix for this with this setup, this matrix of T is going to get you, well, TV1 is going to give you 1, 0. And TV2, well, V2 is in the null space. So you get 0, 0. So with this setup, V1, V2, W1, W2, where this is in the null space, and this is TV1, that's all you can get. With this particular basis, that's the matrix you get. So the question is, well, how can we fix this? I can't just put in a V2 because if V2 is in the null space, it's always going to spit zeros out. So somehow I've got to put V1 into V2 somehow. So that's where this idea comes from. Maybe instead of this, I can use this. Because now these are linearly independent, still a basis, but now T takes both of these vectors and produces an output. Well, what does it produce? So with this basis, T of V1 spits out T of V1 plus 0 of W2s, which gets me the first column 1, 0. And what does T do to the second vector? V1 plus V2 Well, that spits out TV1 plus 0. Oh, look, there's an extra 1. I picked up another 1 here, right? The fact that I put V1 plus V2 means now I've picked up an extra copy of TV1. Man, I'm getting close. Now, almost there, right? Because now, with this modification, I have 1s in the first row. How the hell am I going to get 1s in the second row? And the next idea that might occur to you when you're playing around, and again, much easier to like play games when you're playing with 2 vectors instead of a bunch of them. The next idea you might have is, well, the problem is that this W2 doesn't have any pieces of TV1 inside of it. So maybe what we can do is change this basis. What if we use W is equal to the span TV1 minus W2 comma W2? Because I'm going to show you right now. Now what does T do to V1? Well, TV1 is equal to TV1, but in this basis, that means it's equal to C times TV1 minus W2 plus D times W2. This is a new basis, which means the coefficients have changed, right? Why did I put the minus here? Because this turns into CTV1 minus CW2 plus DW2. What number does that have to be? If it's equal to TV1, what does this have to be? 1. TV1 minus W2 plus DW2 is equal to TV1. What does that have to add to? 0. But if that has to add to 0, what does D have to be? Well, no, there's no C anymore. There's C with 1, right? So what is D? 1. But that means that this was equal to 1 times TV1 minus W2 plus 1 times W2. The minus is there, so these cancel. So that means that the first column is this now. And if we apply this to the second vector, well, that's being thrown away because it's in a null space. And so we're just copying up another copy of TV1. TV2, T of V1 plus V2 is equal to TV1, which we already know is equal to 1 TV1 plus, well, we already know what that is, right? It's just this again. We've tricked this up so that it does this. And my suggestion is it's much easier, while this problem is complicated, it's much easier to figure out what's going on if you do it in the two vector case than to try to work in the n vector case. Okay. Yep.
Why is W1 equals to TV1? Is that how we define T?
This was our first effort at making a basis. Our first effort was, let's let this be a basis for V, where this is in the null space. And for W, let's figure out where the range is, and that like a basis for the range, and then extend it to a basis for all of W.
Okay, so if you define W1 first, that is the basis for range T.
Yeah, this one right here, this is our first effort at doing this. And then our modification of this idea was, well, this gave us a bunch of zeros in the second column. So maybe I can work with it. I have to modify this basis somehow. So build it bigger, more complicated. And our modification of this basis was this idea. I mean, honestly, the best way to do a question like this is just try things and see how it makes the coefficients change. Okay. But like uncovering the fact that there's these relationships between the coefficients on the when you change the basis, the coefficients all have to change in correspondence to the basis changing. Okay. All right, so that was long-winded. Anything else? Oh yeah. What else? I mean, in this case, it was obvious that this is a basis because these are obviously linearly dependent.
Can you ask your questions?
Please.
It's number 16.
Number 16 on
The next,
what?
Everyone asking the same questions I had, except I have the backwards for that one.
For 16. 3D 16.
Correct. I was confused about that.
3D. Hold on, I got some questions. 3D 16. Again, I'm going to open the floor to 16. Suppose V is finite dimensional. Prove that T is a scalar multiple of the identity if and only if ST is equal to TS for every S. Okay, so one direction of this is pretty easy, right? If you happen to know it's a scalar multiple of the identity. Okay. So this is an excellent question. In fact, the solution to this question is just sitting in Slack right now, waiting for your perusal.
It's also in linear algebra, but it doesn't make any sense. I already took a look. I just don't get it.
All right, let's do the easy direction first, right? This is actually one of the major facts about matrices, by the way, is that a matrix that competes with any other matrix automatically is a scalar multiple of the identity. So let's suppose that S is equal to lambda I or some lambda in the field. What it means to be a scalar multiple of the identity, right? Then ST is equal to lambda IT, which equals lambda T, which equals lambda TI, which equals T lambda I, because you can pull scalars around inside of multiplications, which is TS. Okay, I'll just leave the rest to you. Oh no. Okay, actually, hold on. Let me pull up this. You say there's a linear algebra solution to this one, and it doesn't make any sense.
Yeah.
Oh, my favorite. This is 3D. Is that right? See the linear done. What? Oh, this is actually biaxlar. Okay. Oh, yeah. There's your problem. Axler solutions to Axler's own problems are sometimes I mean, okay. Oh, to prove the implications, what is it? We're going to proving that VTV is linearly dependent. Oh my God. Okay. Yowza. That's terrible. All right. Oh, hold on. I'm gonna go up here. I'm gonna take a look at this. Where did that go? I thought, Chandradeep, did you post that publicly, or was that just to me personally? In 306 thread? Oh, there it is. Because I thought that solution was much more elegant than so this was cooked up in the workshop, I believe. So let's look at this one instead. Okay, so if you want to come in and talk to me, and I'll walk you through what's going on in Axler's proof, but it is extremely long-winded. Also, that version of Axler's solutions is like from 1997, which is his first version of the solutions he ever put out. So it's not actually like modified in any way. So here's the solution. I'm going to reproduce the solution that I was told the workshop cooked up. It looks like this. All right, so this is by contraposition. So what we're going to do is we're going to suppose that that we don't have a scalar multiple of the identity. Suppose T is not a scalar multiple of the identity. Okay, so this entire argument is going to pivot off of showing that there exists a single vector for which this thing does not commute. Okay, so if T is not a scalar multiple of the identity, then the assertion is that there exists a vector V in V such that TV is not equal to lambda V for any lambda. It's not a scalar multiple of the identity that you can find some vector that's never a scalar multiple. That's the way I see this written down, right? There exists a V, so the TV is not lambda V for all V. Now, No, I want to notice that this actually pivots off of Axler's proof, because Axler spends a whole lot of time showing that V and TV are linearly dependent. This is just going to assert that these vectors, that V and TV, therefore, or thus, V and TV are linearly independent. Why? They're not scalar multiples. The whole point of this original assertion is that TV is not a scalar multiple of V. I'm going to point out like where I think maybe one more line of argument can take place here. Okay, so now if that's true, if V and TV are linearly independent, then you can say that V and TV can be extended to the basis for V. So V, TV, V3, V4, and the extension theorem. And now we're just going to show that S and T, that there's some S that T doesn't commute with. The statement is that T and S commute for all S. So if I'm trying to disprove that, I just need to find a single S for which they don't commute. Contraposition would be if the forward direction says if what are we even trying to prove here? It's the backwards direction that we're trying to say if ST and ST commute for all S, then we've got a scalar multiple of the identity. So we're doing that by assuming that it's not a scalar multiple of the identity. And we're going to conclude that there exists an operator S that T does not commute with. Okay, so I'm just going to show you what it is. Define S by, let's see what you're going to do here. S takes, S takes all vectors, takes all basis vectors to V. So what I mean by that is SV is equal to V, and STV is equal to V, and SV3 is equal to V. I mean, S is not a very interesting operator. When you extend by linearity, to an operator on all of V. We've used that idea before about defining the function on the basis and then like showing what it does all over the place. And then the final observation here is this function that eats all the basis vectors and sticks V out every single time. If you so impolite. Okay, so then what we're going to exhibit. So if you believe that this is a linear operator, you can prove that this is a linear operator by extension, then you should buy that STV is not equal to TSV.
You have to prove it's linear in the proof.
I mean, I think you don't. I think if you define this on a base, if you ever do this move where you define something on a basis and then extend by linearity, what that means is that you're writing down what it does to any linear combination, that you're forcing it to have the right definition on a linear combination.
Any linear combination of that basis will just have to be.
Yeah, I mean, yeah, well, with the constants pulled out, right? The equivalent way of doing a definition like this is to write S of C1, V1 up to Cn, V, sorry, C2, Cn, Vn. This is the same as saying C1, V plus C2, V plus C3, V, and so on, right? This is the same definition as writing it this way. Every basis vector is being thrown to V. Same idea. But this is when I say extend by linearity, I mean this. Apply S to a linear combination means put S on each of the basis vectors and send them all to V. Why should you believe that's not true? Well, what is this equal to? What does S do to the vector TV? Well, TV is in the basis. What does it do to it? Sends to V. What does S do to V? But V and TV are linearly independent. They can't be equal. These are linearly independent vectors. And so ST applied to B is not equal to TS applied to B. And so therefore T cannot commute with all operators. So the only part of this proof, I like this argument because I'm not sure that this is any less easy to understand necessarily than the long one, but at least the idea is straightforward, right? Which is you're going to exhibit one counterexample as to why the commuting fails. You find the V, you construct the S, and then you show that it doesn't commute on this, right? Which is like when you're exhibiting things, why Axer does it in forward direction is because he's involving a lot of ideas in there, right? His rather expansive proof is showing you lots of ideas about how this construction is happening. And he spends a lot of time with the mechanics of it, as opposed to this sort of, I would say, less enlightening, but easier to understand exhibition of like how this commuting fails. Now, the one part of this that I'm curious about, and your natural inclination in a math class should always be to like disbelieve everything you hear. Like, it should be radical cynic in your math classes. Radical skeptic, not cynic. I mean, of course, it's all pointless. You don't need to be radical about that, but you can at least be skeptical while you're being cynical. This assertion, right, that if T is not equal to lambda I, then there exists a V so that TB is not equal to lambda V for all lambda in F. This is something that's worth taking some time to think about why that might be true. Right? The fact that if you're not a scalar multiple of the identity, then you can find some vector V that T turns into not a multiple of itself. This is worth taking some time to think about. I rather glibly step through that. You probably all sat down there and just wrote it down, thinking like, oh, I'll just write that down. Looks fine to me. It's the way I absorb mathematics too, but think about why that's true. Is it? If you're a radical skeptic, you look at that line and say, I bet I could find one. But remember, I just need a single vector that breaks this. One single vector that falls out of T that is mapped into something that is not a scalar multiple of itself. And then ask yourself what it would mean if every vector V could be mapped into a scalar multiple of itself. What that would mean. And you're not allowed to use anything about eigenvalues and eigenvectors. You don't know those exist yet. Soon, not yet. Okay, so I want you to think about this. Radical. Don't come in here and start talking about the lizard people living underneath Los Angeles in the sewers or anything, right? Just this is like limited scope in your radical skepticism. Okay, if you could convince me that that line is true, and you can have that argument thanks to the workshop. Okay. All right. So now let's talk for 2 minutes about polynomials. What do you need to know about polynomials? I hope this is worth it. I like taking these days where I can slow down a little bit and talk about homework, even if we don't get through very much, because the ideas are pretty complicated. Here's all I really want you to know about complex polynomials. I think I even said this last time. Polynomials. The most important thing about complex polynomials, and in fact, we are going to use when we show that eigenvalues exist, or eigenvectors exist, is every complex polynomial has a root. 0. Whatever you want to say there. That's it. This is called the fundamental theorem of algebra. And what it implies is that every complex polynomial can be factored into linear terms. Because you take out one linear term. We've been using this fact already, right? We have been using the fact that if P of C is equal to 0, then P of Z is equal to z minus c times q of z. We've been using this. Right? The fact that if a polynomial has a 0, then you can factor out this linear term, right? So we've already been using this fact, but it's important that every complex polynomial has a root. I mean, this number right here is either called a root or a 0, depending on what your background is, which class you have to be in, right? But the idea is, how does that actually imply that every polynomial can be factored in linear terms? Well, you do it once and, oh, hey, guess what? That's a complex polynomial. So it has a root, so you can factor it, and you just keep going, right? And if you combine that with the fact that polynomials are determined by their coefficients, it's that every polynomial uniquely factors up to order, like up to arrangement, right? But every polynomial uniquely factors in linear terms. There's exactly one way to factor a polynomial out of linear terms. So since polynomials are determined by coefficients, every polynomial has, every complex polynomial has a unique linear factorization, which is an incredibly useful fact that is not true in the reals. The theorem in the reals is the corresponding theorem for real value polynomials. So if we have a real polynomial, you get linear terms and irreducible quadratics. Which you can think of as being pairs of conjugate roots. So if you're going to have linear terms in a real polynomial, you always end up with like plus or minus complex numbers. So this z squared plus 1 does not have real roots. But because it had real coefficients, if you factor it, the roots for this polynomial will always occur in complex pairs. Okay.
What does it say linear terms?
Irreducible quadratics. So mostly we're going to concern ourselves with complex polynomials because they're so much nicer. Okay, yep. Factorization. Sorry, I know I got a little lazy there. Unique linear factorization. Okay, really that's like you should read the polynomial chapter. It's not a complicated chapter. It's mostly reminding you of things. Oh, I forgot one thing. I know the bell rang. What is the theorem that said, is this homework problem that says odd polynomials must have roots? What is the theorem that says that if you have a continuous function and you're negative somewhere, and you're positive somewhere else, that you must cross to the x-axis somewhere in the middle? No fair if you heard me say it in office hours earlier. The most important theorem in all of calculus, but they don't tell you. Then you get to 412 and you realize literally everything is proved using it. There's this value that happens between this value and this value, which is like in the middle or in, not the squeeze theorem. I'm negative here, I'm positive here. I had to cross through the x-axis somewhere on the way. Intermediate value theorem. If you were negative someplace and you're positive someplace else, you went through 0 in the middle. That's going to be really useful for the question that asks you to prove that odd polynomials must have a 0. Okay.
What does it say pairs of?
Conjugate roots. All right, intermediate value theorem. I know I've probably got 5 minutes of it in your calculus class, but it's literally the most important theorem in calculus. So, all right, I'll see you guys. Is my computer smoking or is that dust? That's just not smoking.
Would you say it's more important than the mean value theorem?
Well, you can't have the mean value theorem unless you have the intermediate value theorem. So